right. All right, y'all. Welcome back. Any questions before we get started? All right. For those that are in here already, here are the notes we're going to cover. Let's see. Oops, desktop. Let's see. There you go. Okay, So we're going to cover 9.3 today. But again, does anybody have any questions before we get started? Here is the PDF again for whoever's just joining us. So download it, follow along, and let's do this. All right. So today we cover continuity and the definition of continuity. There are 3 rules to continuity. So a function f is continuous at the point x equals c if the limit of f of x exists, 2, the point f of c exists, and 3, the limit as x approaches c of f of x is equal to f of c. So in order to be a fully continuous function, you have to pass these 3 rules. So we must pass these 3. If you fail one rule, then it throws everything out and the function will be considered discontinuous. So we are going to practice the rules of continuity today on given values of x. Okay, so let's go ahead and explore example 1 down below. So for number 1, it says use the definition of continuity to discuss the continuity of the function at x equals 1. So we're going to be looking at the x value of 1 and what is going on there. So for part A, it says find the limit as you approach 1 from the left. So as x gets closer and closer to 1 from the left, y is getting closer and closer to what number?
4.
4. Good. So this will be 4. The limit from the left is 4. This is the PDF for continuity. Did I send the right one? Here, I'll send. Oh, I probably sent the wrong one. Sorry, I said 9.1. Ha. Here you go, 9.3. There you go, continuity, better. Okay, cool. So the limit from the left at 1 is 4. So now question B says, what is the limit as x approaches 1 from the right of f of x? So as you approach 1 from the right, y is getting closer and closer to what number?
1.
1. Good. So the limit from the left is 4. The limit from the right is 1, which brings us to question C. Question C says, what is the limit as x approaches 1 from both sides of f of x? So if the limit from the left is 4 and the limit from the right is 1, those are not equivalent. Therefore, does a limit actually exist?
No.
No. So once again, the limit from the left is 4. The limit from the right is 1. These are not equal, so therefore, the limit from both sides does not exist. Okay, so what does that mean continuity-wise? Well, let's go back up and look at the rules of continuity. Maybe I could just zoom this out. There we go. Look at number 1. In order for a function to be continuous, a limit from both sides at some value of c must exist. Well, we just saw here that rule number 1 has just failed because we see that the limit as x approaches 1 from both sides does not exist. So this means that this is a fail. And if one condition fails, if one rule fails, then the whole function becomes discontinuous. So we have failed one rule, meaning we throw all the other rules out because it's not going to matter, and therefore our function is discontinuous. So we fail, which means we can say at x equals 1, f of x is discontinuous. Okay. But let's keep going. Let's answer D and let's answer E, which we probably just answered E already. But let's go ahead and go to D. And let me get rid of all of this. D says, find the function value at f of 1. So this means that when x is exactly 1, what is the value of y? And if you see here, we have two values for y. Which one do you think we state? 4 or 1?
4.
4. Why?
1, it's like a hollowed circle, so it's not actually a part of it.
Good. So very good. So the reason we do not state this point is because it's an open circle, meaning we cannot state this point because it's an undefined point. This one we state because it's a closed circle, meaning that that value is defined. So this is why we only state the y value of 4 when x is 1. Okay. Which, again, by referencing the rules of continuity, that would actually be a pass. Because what rule 2 says is the point must exist. So this point exists, which would be a pass. But once again, it doesn't matter because we already failed rule 1. So if you fail one condition, it throws the whole thing out. Okay. And then the last question, E, is the function continuous at x equals 1? And I think we answered that when we answered C. So why is this function not continuous?
Because the limit doesn't exist.
Good. That's it. We said it right there, right? At f of x, or at x equals 1, f of x is discontinuous because the limit does not exist. There we go. So that is just a practice in the rules of continuity. So for most of your homework problems, you're always going to discuss why something is discontinuous. If you were to discuss something being continuous, well, that would just be way too easy. But yes, you can use the rules of continuity on continuous functions and discontinuous functions. So it's just a practice in how to use the rules. That's why we mainly look at discontinuous parts of a function. Okay, so those are the rules of continuity. Any questions on that page? All right. All right. So more about continuity. So one of the ways to find the continuity of a function is to know the type of function you are given and also to know the domain of the function you are given. So rules, or for theorem, properties A through F they just talk about what type of functions there are and where they are continuous at. So if we start at A says a constant function f of x equals k, where k is a constant, is continuous for all x. So if you're ever given a constant function, this means that your function will be continuous for all values of x, meaning your domain would be all real numbers. So let me go ahead and write an example for that one. For A, I'll go over here. If I was given a continuous function, it would just be f of x equals a constant. And remember, a constant is just a number without a variable. So let's just say f of x equals 5. And now, if I were to graph that, f of x equals 5 is basically the same as me saying y equals 5. What type of line would that make? A horizontal or a vertical line?
Horizontal.
Horizontal, good. So you would have a horizontal line like that. where this tail would go to negative infinity and that tail will go to positive infinity, meaning that since this function goes on infinitely, 1 towards negative infinity, 1 towards positive infinity, this means that by the definition, by the property, a constant function will be continuous for all x. Continuous for all x. That's all it means. So if I were to write the domain of A, I would say the domain, since we saw it goes to negative infinity and positive infinity, we would say the domain goes to negative infinity, positive infinity. Or another way to state that in continuity terms is continuous for all x. That's all it means. It doesn't stop, and there's no breaks in the graph. Okay. Now, property B. For n, a positive integer, f of x equals x to the power of n is continuous for all x. Okay, so let's get some basic definitions out of here. First off, a positive integer. So just know that a integer is a whole number. An integer is a whole number from negative to infinity. But this one says it wants positive integers. So a positive integer is a set of whole numbers from 1 to infinity. So this means that if we are given a function that has a positive integer as an exponent or as a degree or as a power, this means that it will be continuous for all x. It would share the same domain as A. So a good example of that, let's say for B. Let me change color. There we go. I just was given f of x equals x squared. So here, 2 is a positive number. 2 is a positive whole number. Therefore, 2 is a positive integer, which means if you thought about the graph of x squared, it would look something like that. And one tail would go to negative infinity. The other tail would go to positive infinity. Therefore, sharing the same properties as A. The domain would be all real numbers, and it would be continuous for all values of x. So again, I can say domain, negative infinity to infinity, and then we can state the same thing here, continuous for all values of x. All right. So that's A, and that's B. And now C is just going to be like A and B. A polynomial function is continuous for all values of x. So here we have to know, what does it mean to be a polynomial? And does anybody know what it means to be a polynomial? And it's okay if you don't. To be a polynomial function, so in order to be a polynomial function, your exponents or your degrees or your powers, whatever you guys call them, they all must be positive integers. They all must be positive whole numbers, which means in this case, x squared is considered a polynomial function. So again, to say it again, a polynomial function, to be a polynomial function means that all your exponents have to be whole positive numbers. That's it. There's no other criteria. If it was x to the first, x squared, x to the 100th, these are all whole positive numbers. If it was x to the 1/2, would that represent a polynomial?
No.
No, because it's not a whole number. So to be a polynomial function, your exponents must be whole positive numbers. Okay, and to explore an example of that, well, let's go ahead and look at the first example below, down here. Look at that function. F of x equals x squared minus 2x plus 1. Now, Does that look like a polynomial function to you?
Yes.
Yes.
Yeah. All the powers are whole numbers, right? You got a 2 there, you got a 1 there, and you even have a constant on the end. That is a polynomial function, which means that now we know the name. This is a polynomial. And just like A and B, a polynomial shares the same properties as those two. The domain will be all real numbers. And we can say continuous for all x. And I'll say C is here. There you go. Okay. Not bad. So A, B, and C all share the same types of properties. Okay. Move on to D. D says a rational function is continuous for all x, except those values that make a denominator 0. And remember, a rational function, rational is just a fancy word for fraction. So for D, we are going to explore the next example on the right. F of x equals x over x plus 2 times x minus 3. Now, once again, rational is just a fancy word for fraction. And what we have here is a fraction, which means that first off, label what you have. This is a rational function. And in order to find the domain of a rational function, you must take the denominator and set it equal to what number?
0.
Good, 0. X plus 2 times x minus 3 equal to 0. Solve for x, and what are my values of x?
-2 and +3.
Very good. Okay, but we have to understand something from a rational function is that can x actually be equal to these numbers? And that answer is no, because if I were to plug -2 in, or if I were to plug +3 into the denominator would become what number?
0.
0. And can we have that?
Not in the denominator.
Not in the denominator. Okay. So now we have found the domain of this function. Now let's state where it's continuous at. And to show you where it's continuous at, let's just go ahead and draw a number line really fast. So here's the number line that will represent this function, this rational function, -infinity to infinity. And I'm going to plot the numbers that we just found. Here's -2, and here's +3. So now when I state its continuity, let's go ahead and state it in intervals. So we're going to say continuous on, and when I put this into interval notation, what is the smallest number that we start at?
-infinity.
-infinity. And then we come up the number line, but where do we stop at?
-2.
-2. Union, where do we start at again?
-2.
Good. So we just went that way. We have to stop, and then we start again at -2, and then we have to stop where? And then we start again at what number?
3.
3, and head towards where?
Infinity.
There you go. So what we're stating with this interval is not only the function's domain, but we're also stating where this function can be continuous on. We are stating that, hey, this function can be any number it wants to be, except for -2 and 3. Except for -2 and 3. So our function can exist from negative infinity to -2, -2 to 3, and 3 to infinity. All right. Okay, and that's how you handle a rational function. But this is stuff we know already, right? The only calculus we're applying to this is the word continuous. That's it. Okay, now let's go for E. For n, an odd positive integer greater than 1, the nth root of f of x is continuous wherever f of x is continuous. So E, the property E belongs to odd rooted functions. Odd rooted functions. So the cube root, the fifth root, the seventh root, the ninth root, any odd number. So if you ever have an odd root, you are continuous where the inside function is continuous at. So if we apply E to the next example, well, let's go ahead and look at it. Here we have the cube root of x squared minus 4. So again, we're going to state the name. This is an odd radical, or you could even say odd root function. So odd radical. And in order to find the domain of an odd radical, we have to understand some things about odd radicals. So let's just look at the cube root because that's what we're given. So let's think about the cube root for a second. Can you take the cube root of a positive number?
Yes.
Yes, good. Can you take the cube root of 0?
No.
Think about it. What do you think the cube root of 0 is?
0.
0. So that's a yes, right? And now the last tricky part. Can you take the cube root of a negative number? So let's just go over everything I talked about so far. Cube root of a positive number, let's just choose 1, for example, would be 1. Cube root of 0 would be 0. Cube root of -1. Can you take the cube root of a negative number?
No.
Once again, tricky, tricky. The answer is yes. Guess what the cube root of -1 is?
1.
-1. So what we're saying with this is that with the cube root or with any odd root, you can take the odd root of a positive number, you can take the odd root of 0, and you can take the odd root of a negative number. This means that for an odd root, we can take the odd root of whatever number we like. So that means there are no restrictions on numbers we could use. So what would the domain of this function be?
All real.
That's it. Which means we can again state continuous for all x. Crazy, right? All right. Last one. F. You belong here. Okay. Well, if E dealt with odd roots, then F is going to deal with even roots. So for n, an even positive integer, the nth root of f of x is continuous wherever f of x is continuous and non-negative. So that means if you have an even root function, we're going to be continuous wherever we are non-negative. So let's explore what that means. So over here, we have now an even radical. And to find the domain of an even rooted function. And what's it mean to be an even root? It means you have the square root, the 4th root, the 6th root, the 8th root, the 100th root, whatever number, as long as it's even. So here we are just given the square root, thank goodness, right? So let's look at the square root of x just as an example. And let's talk about what we know about the square root of x. First off, once again, let's start. Can you take the square root of a positive number?
Yes.
Yeah. Square root of 1 would be 1. Then, can you take the square root of 0?
Yes.
Yeah, you'd get 0. But then, could you take the square root of -1?
Yes.
This one, well, technically, yes, but since we're business majors, we don't want this type of answer because the square root of a negative number will give us something that's called imaginary numbers, which we want to avoid. So putting that together, a square root, an even root at that, can only take the square root of 0 and above. So for any even rooted function, you take whatever's inside the house, and to stay above 0, what inequality would you write?
Greater than 0?
Good, greater than 0. But since we can take the square root of 0, we're not only going to put greater than, we're going to put greater than or
Equal.
equal to 0. Because we are allowed to take the square root of 0, therefore it's greater than or equal to. And now all we have to do is solve for x. And there's our domain, which tells us where we are continuous at. This says that this even rooted function is going to be continuous for any x value greater than or equal to 2. So I'll say continuous on, and how would I put x greater than or equal to 2 into interval notation? What number would I start at?
2.
2. And what type of notation would that get? A parentheses or a bracket?
Bracket.
Bracket. 2. And if we have to be greater than 2, where are we headed?
Positive infinity.
There you go. And that's it, guys. Well, for that page. So to keep that page really, really simple, if you know the domain, well, first, if you know the function you have, and if you know the domain of that function, then in calculus terms, you know where you're continuous on. That's it. So looking at domains, this should be nothing new to you. But if it was, that was a good refresher then. Any questions on this page before moving on? All right. Not bad. Okay. So the next page deals with creating a sign chart to solve an inequality. So I'll read you the theorem real fast and try to break it down into English. The theorem, sign properties on an open interval AB. If f is continuous on an open interval AB and f of x doesn't equal 0 for all x in AB, then either f of x is greater than 0 for all x in this open interval, or f of x is less than 0 for all x in this open interval. So to put it into English, what we're going to do is we're going to create a sign chart, basically a number line. We're going to find x values given from the function. And what we're going to do is take these x values, plug them back into the function, and all this is going to tell us is where are we above or below the x-axis. That's all we're going to do. Don't worry, it's not that crazy. Maybe just a little bit. Okay, so whenever it says f of x greater than 0 or f of x less than 0, all that wants to know is where are your y values above the x-axis or where are your y values below the x-axis. That's it. Okay. And then I'll keep that up for the next definition. A real number x is a partition number for a function f if f is discontinuous at x or f of x equals 0. So once again, when we solve for values of x on the given function, we're going to plot those on a number line. And those numbers, those values of x, are also known to be partition numbers. So whenever I drew this funky graph over here, this would be a partition number, and that would be a partition number because they break up the number line. Okay, now let me get rid of crazy picture because we're going to make our own sign chart. And the reason why we're making this sign chart is because once we get into chapter 2, or no, not chapter, but test 2 or test 3, we're going to be making a ton of sign charts. So it's good to see it now, so later you're better prepared. Okay, so let's start example 3. It says solve an inequality by constructing a sign chart. Express the solution in inequality notation and interval notation. Okay, so for number 1, well, the only one on example 3. Okay, so this says x plus 1 over x minus 2 greater than 0. So before we even begin, we want to know what it's asking us. And what this inequality is asking us, it's because it's gonna deal with the final answer. So this says, where are we greater than 0? Basically, this is saying, where are we above the x-axis? So where is this function above the x-axis? And now we're going to do a bunch of work just to answer this simple question. So let's do this in steps. Step A, the first thing we're going to do is solve for the domain. And since this is a rational function, what am I going to set the denominator equal to?
0.
0. And look at this, guys. We get our first x value. X equals 2. But once again, can we actually be equal to 2? What happens if x is 2? What happens to your denominator?
Becomes 0.
Becomes 0. Can we have that?
No.
No. All right. So we find the domain, and then we move on to step B. Step B, we're going to find an X-intercept. Well, I'm going to make your work really, really simple for these problems. So domain, so whenever you're given a rational function or expression, the denominator will always give you the domain. The numerator will always give you the X-intercept. So whenever you're solving for a domain, set the denominator equal to 0. And whenever you're solving for the X-intercept, set the numerator equal to 0. Makes the work a lot easier. Okay, and then move that over, and x equals -1. I'll say it one more time, right? Domain comes from the denominator, X-intercepts come from the numerator. Okay, and let's go ahead and look back at that definition of a partition number. A partition number for a function f, if f is discontinuous at x, well, hey, look at that. If we are discontinuous at x, this function doesn't exist at 2. Therefore, x equals 2 is a partition number. Or f of x equals 0. Hey, if I plug in -1, the function becomes 0. So these are partition numbers. They follow that definition. All right, just wanted to explore that definition a little more with you. Okay, and then next is, let's go ahead and make a sign chart. There we go. Here's negative infinity. There's positive infinity. Let's go ahead and plot the numbers we just found. Here's going to be -1. And over here is going to be 2. Notice that -1 is closed circle and +2 is open circle. Because we can be equal to -1. We can't be equal to 2 because that's what the domain says. Okay. And the next part for our sign chart, we're going to make intervals. Get all the colors. There we go. We're going to make intervals based on our sign chart. So I'm going to start, I'm going to start with -infinity to -1, -1 to 2, and 2 to infinity. These are all the intervals I'm talking about. That's what I just wrote down. Okay.
Why do these not have the union symbol?
Very good. That is a very good question. The reason these do not have a union or proper bracket notation is because we are not stating domain. We are only stating intervals on a number line.
Got it. Thanks.
So, good question. That's a good question. Okay. So what we're going to do next is pick test numbers between each interval. So I'm going to say test numbers. And now for the first interval, -infinity to -1, somebody give me a test number for X.
Does
-2.
it have to be in the parentheses?
Has to be within the numbers. And I just heard -2.
Yep.
Good. Then give me a test number from -1 to 2.
1.
1. Good. 1 works. You can choose 0 as well, but let's go ahead and choose 1. And then give me a number from 2 to infinity.
4.
4. Okay, cool. 400. 400 would work as well, as long as it's in the interval. All right. So what we're going to do next is take all these X values and plug them into this function. And all we're really going to care about is the sign of the output, whether that output is positive or negative. So let me do this. I'll say y equals, y equals, y equals. All right. And to plug these numbers in, to make quick work of it, I'm going to go ahead and use this Desmos program I always talk about. Move that there. I'll put this here. Hey, and look at that. I already have the function up. X plus 1 over x minus 2. But to show you guys how to type it in, so if you go to desmos.com and use the graphing calculator, I'm going to type this function in. I'm just going to hit divide, and then I'll say x plus 1 over x minus 2. And then to get the table feature up where I can plug my numbers in, I'm just going to hit that little gear icon right there above the X in this little box. So that gear icon, and then you'll see the little table. I'm just going to click that, and there you go. And now all I'm going to do here, oops, let me go to this side, is type in the numbers exactly. Hey, look at that. -2 is there for us already. So -2, I get 0.25. Is 1 there already? Sure is. 1, I get -2. And then if I'm going to type in 4, I'll just type 4 on this table, hit enter, and I get 2.5. There you go. Or if you like, plug them in one by one and figure it out. Okay, so that's Desmos. Now let's go ahead and look at what we have here. So I'll just keep that up. So the test number we picked from -infinity to -1 was -2. And whenever we plug that into the original function, we got a positive output. So like I said, we're only looking at the output, whether it's positive or negative. So if you have a positive output, this means that no matter what X value you pick from -infinity to -1, you're always going to get a positive output, meaning your Y values will always be above the X axis. And then we picked the next interval, -1 to 2. We picked a test number between there, and we got a negative output. This means that no matter what number you choose between -1 and 2, your Y values will always be below the X axis. And then, do you believe in patterns? Sure, right? The last output was positive, meaning that no matter what X value you pick from 2 to infinity, your Y value is always going to be positive, which means we will be above the X axis. And I can prove that to you using this little chart over here on the left. Let's say we choose 4. Let's say I choose 400. Let's say I choose 10,000. You see that? The output on the right is always positive no matter what. So it doesn't matter what test number you pick, as long as it's in the interval. Okay. I'm gonna come back to the notes screen. And now, I guess I should put what these mean. So this means above x-axis and below x-axis. Okay. So D, to answer the final question, what we were asked above. This wants to know on what intervals is our rational function above the x-axis. So I'm just going to say r of x greater than 0. And now look at your sign chart. And on what intervals are we above the x-axis?
-infinity to -1.
And where else?
2 to infinity.
There you go. That's our answer. That's what that wanted. All that work for that one simple answer, right? Okay. So for my math lab, it may not take the union. It just might take the comma, because union is when you're stating domain. And once again, we're not stating a domain here. So it might take a comma. So here, I'll write that over here somewhere. I'll say MML might be just -infinity to -1, comma, 2 to infinity. I guess you'll see when you're typing them in.
And this won't take the bracket notation.
Oh, good question again. Why don't we have a bracket? What's the inequality?
Oh, okay, it's just greater than, not
It's just
greater
greater
than or
than.
equal to.
If it was greater than or equal to, then yes, you would have -infinity to -1 bracket. Good. That's a good question. Oh yeah. This said write it into inequality notation. So actually, let's go ahead and do that as well. So let's look at the first one. This says our interval is negative infinity to -1. This means that all your x values must be less than -1. So how would I write that? I mean, I just said it. So what would I write? X is what? What do you think? If your interval is from negative infinity to -1, is x going to be greater than or less than -1?
Less than.
Less than.
What's that?
Good. And then to rewrite this into inequality notation, our interval is 2 to infinity. This means that you'll start at 2 and you'll go greater than 2 towards infinity. So I would write x has to be what?
Greater than or equal to.
Just greater than 2. No equal to because there's no bracket. And that's it. That's interval and inequality. Okay, perfect. That was fun. Any questions on that page before moving on? All right. Last page. I promise. We made it. All right. Example 4. Graph f, locate all points of discontinuity and discuss the behavior of f at these points. So here we're given a piecewise function again. F of x equals x squared if x is less than 1, and f of x equals 2x if x is greater than 1. Graph the function, create xy charts for each part of the piecewise function. So one of the easiest ways to graph a piecewise function is to make separate xy charts for each function in the piecewise. So what we're going to do is first, I'll make an xy chart for x squared. And I'll just say x and y equals x squared. And right above it, I'm going to put the restriction. X has to be less than 1. I put the restriction up there because that's telling us what numbers we have to use. So x has to be less than 1. I'm going to start at 1, and I'm just going to go less than 1. So if we go less than 1, how about 0, -1, -2, -3? And take all these values and plug them into x squared. So basically you're squaring all of these. So you'll get 1, 0, 1, 4, 9. Okay. But I have to stop here for a second because can I actually use this point?
It's got to be greater than.
It's got to be less than, right? It doesn't say less than or
Equal to.
equal to. So what this point is going to be considered when we graph it is undefined. Okay. But we actually need this point. That's why I include it. It has to be our starting point no matter what. Okay. And then we'll go ahead and graph 2x. So same process. X and y equals 2x. Put the restriction right above it. X greater than 1. And again, I'm going to start at 1. And I'm just going to go greater than 1. 1, 2, 3, 4, 5. And I'm only going up to these numbers because that's all that's going to fit on our graph. Plug these numbers into 2x and you'll get 2, 4, 6, 8, 10. And again, pause for a moment because can we actually use this point?
No.
No, because once again, our inequality says greater than 1, not greater than or equal to 1. So that will be undefined as well. Okay, let's go ahead and graph. I've got room over here. Perfect. And I'll graph the first one. Here's 1, 1, which is going to be an open circle. And then 0, 0, negative 1, 1, negative 2, 4, negative 3, 9. Here is our first function of the piecewise function. And then I'll graph the green function, 1, 2. That's going to be an open circle as well. And then 2, 4, 6, 8, 10. There we go. Oh, here, and I'll make this as 1. That's all we really need there. Okay, now, based on our graph, let's go to B. And where does it look like we have a point of discontinuity? Basically, where is there at what X value is there a break in the graph?
1.
Good. At X equals 1, f of X is discontinuous. But let's go ahead and prove why it's discontinuous. Which may help out in C, because C says find any Y values at the point of discontinuity. Well, when X is 1, can we state any Y values?
No.
No, because both points are open or closed?
Open.
Open. Therefore, at X equals 1, no Y values exist. Or actually, to put it better in words, no Y values are defined. Because since we're in calculus, we say limits do not exist and points are undefined or not defined. So I guess we could just say Y values are undefined. Okay. And then the very last question says, find the limit as X approaches C of f of X, where C is the point at which f of X is discontinuous. Okay. So in order to see if we have a limit that exists, we need a left-hand limit and a right-hand limit. So let's just look at the graph above. And let's go with this. Let's just look at this one. So as we approach 1 from the left, Y is getting closer to what number?
I'm sorry, what?
Just run that back. Because we want to know if a limit exists at this point of discontinuity. So in order for a limit to exist, we need to prove that there's a limit from the left and a limit from the right. or prove that by using a limit from the left and a limit from the right. So here, if we approach 1 from the left, y is getting closer and closer to what number?
1.
1. Okay. And then if I said, what is the limit as we approach 1 from the right? So as you approach 1 from the right, y is getting closer and closer to what number?
2.
2. And now, if I said, what is the limit as x approaches 1 from both sides, what would the limit be?
Doesn't exist.
Doesn't exist. Why?
They're not equal.
These are not equal, right? Further proving that, yes, this function is definitely discontinuous at x equals 1. So I'll just write that down here. The limit as x approaches 1 from both sides does not exist. And that's it. Any questions on that?
Is this on the homework due Wednesday or is it different?
Remember that every time we do a lecture, that homework is, so since we just did 9.3 today, you have a week to do 9.3. So this homework won't be due till next Monday.
So we have a homework assignment for each lecture?
Exactly.
Okay.
So 9.1 we did on Wednesday. So 9.1 will be due on Wednesday. This Wednesday. So this means that you guys can get started on 9.3 today. Or finish 9.1 if you have not yet. But other than that, we are done. There's some time left if you have questions. If not, if you're all good, then I will see you on Wednesday.